In this video, we are going to be looking into nature of matter. My expectation from you is that at the end of this video of topic nature of matter, you are able to define matter and states of matter, differentiate between the states of matter, use diagram to illustrate change of states, and also differentiate between physical and chemical changes. We are going to look into definition of matter, the three states of matter, and also going to look at the change of states of matter, and the last we are going to look into physical and chemical changes. Matter is anything that has mass and can take a place. These include iron rod, sugar crystals, rocks, human or animals, water, oil, bromine, air, hydrogen, etc. Things like wave, energy, rays, spoken word are said to be non-matter because either they don't have mass or they can't take a space. A question: why is lion, bottle, and air said to be matter, but energy not a matter? The answer is each of them, lion, bottle, air, has both mass and can take a space, whereas energy does not take a space, and we also believe that energy does not have mass. State of matter is how matter appears to exist at room temperature. In chemistry, we have 5 states of matter, but the major is 3, which are solid, liquid, gas. Matter is regarded as solid if it exists as solid at room temperature. This means that its melting point is above 25 degrees Celsius or 298 Kelvin. Examples of substances that exist as solid at room temperature include: all metals except mercury exist as solids. Examples of metals include iron, copper, gold, platinum, sodium, calcium, magnesium, etc. Or we still have non-metals like sulfur, carbon, phosphorus, and iodine that exist as solid at room temperature. And all metalloids exist as solids. Examples of metalloids include silicon, germanium, etc. What about compounds? All ionic compounds like sodium chloride, calcium oxide exist as solid. We still have something like sugar crystals, plastics, and so on. Okay, let's look at the mixtures that can exist as solids. For mixtures, we have alloys of metals like bronze, steel, brass. We still have something like physics. We have wood, we have coal, and many more. One of the property of solid material is that their properties are well packed and well arranged, and this arrangement is done in crystalline or amorphous form. That is why as you go further in chemistry, you will understand that something like ionic compounds are mostly in crystalline forms. Metals are mostly in crystalline forms. Now when we have something like carbon, we have something like silicon, we have something like sulfur, we have amorphous allotropes and crystalline allotropes of carbon or sulfur. When we go further, you will understand that. Their intermolecular forces holding solid particles are strong enough to hold them together. That is the major reason why their particles are well packed and well arranged in crystalline or amorphous form, is because there is a great intermolecular force holding the solid particles. Having a strong molecular force holding them together gave rise to them to have a definite shape and also have a definite volume. This means that the entropy is going to be very low in solids. They are not easily compressed. What I mean by this compression is pressure does not easily act on it. They are very rigid and cannot flow. This is because the particles cannot slide over one another. Since it is not easy for the particles to move around because they only vibrate when they gain kinetic energy, that means that they have the least kinetic energy. Remember, they don't move much and they don't have disorderliness. Since they don't have much disorderliness, we group them as the one that have the least entropy. Since entropy means disorderliness of a system, understanding that the solid particles are well packed, it means that they don't have much space between fellow particles. That means that among all the three states of matter, solid possess the least space between fellow particles. Solid particles density is mostly high. If you understand that the particles are well packed, and you understand the intermolecular force holding the particles are very strong, and if you understand that it is not very easy for them to flow, it means that diffusion, which is the ability of the molecules to move from where it is being concentrated to where it is not concentrated, that is lower concentration. This makes it easier for us to understand that diffusion in solid is the slowest among the three states of matter. When the solid particles are heated, what only happens is that the particles only vibrate with one another. They don't translate. So, for us to assume that a particular matter is liquid, it means that the liquid exists as liquid at room temperature. And one more thing here is that its boiling point must be above 25 degrees Celsius and its melting point below 25 degrees Celsius. Examples of substances that exist as liquid at room temperature is bromine and mercury are the only two elements that exist as liquid at room temperature. Take note of this. Bromine is a non-metal, whereas mercury is a metal. Examples of compounds that exist as liquid include all acids. Example like hydrochloric acid. We still have something like oil, lower members of alkanol, lower members of esters. For mixtures, we have solutions of ionic compounds. We still have something like palm wine, because palm wine is mixed with water, petroleum, we have blood, and we have urine. Let's look at the properties of liquid. But one thing I just want you to understand here is that properties of liquids are in between solid and gases. Therefore, we go gradually. The particles of liquids are weakly packed and they can slide over one another. The intermolecular forces that is holding liquid particles are not as strong as that of solid particles. They have definite volume, but no definite shape. What they do is they take the shape of the container or the vessel. They are not easily compressed. That is to say, pressure does not really act on this easily. Normally we put it that pressure has no effect on solids and liquids. They are not very rigid as solid are, and they can flow. Since they can slide over one another, it means that they can flow. They possess greater kinetic energy and entropy than that of solid particles. Yes, you notice that they can actually slide from one another. That means that they can translate, not only vibrate with one another. There are spaces where they are trying to close, which is not easy for them to close the spaces. You need to understand that the properties of liquid is between the solid and gases, as I said earlier. Therefore, the space between particles are lesser than that of gas when we come to liquids, but it is greater when we compare it with solid particles. When we come to being heavy, liquid is heavier than gas. That is what we mean by the density. Diffusion, since it can vibrate and slide, it is possible that it can move away from where it is being placed. Okay, this makes it easier for it to diffuse higher than or faster than solid particles. When heated, the liquid particles will vibrate and also translate. That is, they have the ability to vibrate like solid, and they also have the ability to translate like gases. But it's just that their vibration is greater than that of solid, but their translation is lesser than that of the gases. To consider a particular matter to be existing as gas, it means that it exists as that gas even at room temperature. This points that the boiling point and the melting point of this particular substance must be below 25 degrees Celsius. I hope you know what we mean by 25 degrees Celsius. I can change it to Kelvin as 298 Kelvin. Examples of matter existing as gases at room temperature include hydrogen, fluorine, oxygen, nitrogen, chlorine are non-metals that exist as gases. Hydrogen is H, fluorine is F, oxygen is O, nitrogen is N, and chlorine is Cl. That is the symbol. And there is a code I use for this. I call it He, Fon, Klein. They are non-metals that exist as gases, and also all noble gases like helium, neon, argon, and krypton. They exist as noble gases. The next one is the compounds that exist as gases. Mostly covalent compounds like sulfur 4 oxide, sulfur 6 oxide, carbon 4 oxide, ammonia also included. And we can just say all oxides of non-metals are example of compounds that exist as gases. We still have something like all hydrocarbons in which their number of carbon is below 5. We have methane, we have ethane, we have ethene, we have ethane. There are many more of that. We can have something like propane, we can have propene, we can have propine. We can still have something like butane, we can have something like butene and butane, and etc. All of these I mentioned are actually gases at room temperature. and they're actually called hydrocarbons. If you look at it, you see the only element that are found there is carbon and hydrogen. Carbon and hydrogen. That's what I mean by hydrocarbons. Hydrogen and carbon forming a compound. For mixture, I will use air. Air is an example of mixture that has its existence to be as gas. Let's look at the properties of gas. The particles are scattered and spread apart. 2. The intermolecular forces holding gas particles are negligible, or we can even say that the forces are very weak. They have indefinite volume and indefinite shape. You can compare that with that of solid and liquid, and you see that in solid we have definite volume and definite shape, but in liquid we have definite volume but indefinite shape. But here for gas we have both indefinite volume and also indefinite shape. They are not rigid and they can flow most easily. They possess the most kinetic energy and entropy among the 3 states of matter. The distance between gas molecules are very far apart if you actually give them that opportunity. We have the most diffusion rate in gases. When the temperature of gas particle is increased, it is also going to increase the average kinetic energy and pressure of the gas particle. This actually means that if we increase the temperature of gas by heating, they are going to gain more kinetic energy. They will vibrate, they will translate, and they will be moving around. When they hit with one another, they will be moving randomly. Now, when they hit with the wall of their container, they will be having pressure exerted on the wall of their container, and the pressure they exerted in the wall of the container depends on how the temperature or how much energy they gained. The more the energy gained, the more the pressure exerted, and the more the pressure they exert on the wall of the container is actually proportional to the temperature of that particular gas at that time. I would like you to answer the following question in respect to what you have learned in this session. Watch the screen very well. You will notice there is a change. There is a change. That means that before, this word was not here. Now it is there. I hope you got that. Okay, that is what we mean by change. Here I will define change in chemistry as rearrangement of particles of matter. It can be transformation from one form to another. A change of state means a transformation of matter from one state to another due to varying temperature. A varying temperature will result to change in heat. That means that change in heat actually causes what we call change of matter. And we have 6 types of change of matter we are going to discuss. For solids, we have melting and sublimation. For liquids, we have freezing and evaporation. For gas, we have deposition and condensation. This is when a solid changes to liquid directly. Example, ice block giving yield to liquid water. It means that the water in ice gained kinetic energy After vibrating for a long time and more energy is being added to it, it will start to translate because the particles start to slide over one another. Another one is what we call melting of candle wax. You should understand that the opposite of melting is freezing, and that particular point of temperature by which a solid becomes liquid is called melting point. Also, that particular point liquid becomes solid is called freezing point. That temperature by which a solid starts to become liquid is called melting point. It is also equal to the freezing point of that particular substance. The temperature change remains constant. That means that if the temperature was 100 degrees Celsius, it remains 100 degrees Celsius for a long time until all the solids becomes liquid. Then the temperature can move away from 100 degrees Celsius to any other degree Celsius. It is actually called latent heat of fusion for melting point. Let's go for sublimation. Whenever a solid moves to gas directly without passing through liquid, it is named sublimation. Substances that can actually do this include ammonium chloride, naphthalene, camphor, iodine. They become vapor when heated. Note, the opposite of this is called desublimation, but better called decomposition. The last to discuss in this change of state is evaporation or boiling. Whenever a liquid substance turns to gaseous state when heated, we call this evaporation. But if it is in a closed system and a liquid matter is heated, there will be at a particular point when there will be no change in temperature. That no change in temperature signifies the boiling point of that liquid. At that particular point, the vapor pressure of that liquid that is forming gas is equal to the atmospheric pressure. That is why if the atmospheric pressure is low, the boiling point is going to be low. If it is high, the boiling point is going to be high. The opposite of evaporation is called condensation. Relationship between evaporation, sublimation, and melting. Okay, you can see how I represented each of them. The diagram here try to show change of state. This is a change of state diagram. We really need to understand what each of the points represent. To say here, A is still solid. At B, we are going to have what we call melting point. And at melting point, there's not going to be increase in temperature. That is why you have this to be horizontal with x-axis, as you see it over here. Now, when all the solid have converted to liquid, that is when we will start to notice a temperature change as the heat keep on coming over, as we keep on heating the liquid. Something like water, we normally use water for this as an example. And when you heat it to at a point at the boiling point, you start to notice that the water will be converted uniformly to gas. At this position, the temperature also remains constant. This change of matter. Two major changes which matter undergoes, and in chemistry we refer it as physical and chemical change. A change is said to be physical change if the change is easily reversed by ordinary physical means, because no new substance is formed. We have examples of physical changes. Examples of physical changes include change of states, where we have something like melting, condensation, evaporation, sublimation, deposition, and freezing. That is to say, something like melting of candle wax, sublimation of naphthalene, something like freezing of water, evaporation of water, deposition of iodine vapor, and condensation of steam are example of physical change. We also have something like dissolution of all salts. These include dissolving sodium chloride in water, and we can recover it by evaporation. We also have dissolving magnesium tetraoxosulfate 6 in water. We can also recover it. We still have something like crushing of cans, mixing of sugar, flour, and water. For instance, somebody that want to bake bread or any stuff like that. We still have color change of zinc oxide. And a physical change is actually a temporal change. It does not truly require change in heat to happen, except when we are talking about something like change of states and other few examples. Therefore, we are going to look into the chemical change. A type of change where the change can be reversed easily by ordinary physical change, and no new substance is formed, we take it as physical change. But when this change is not easily reversible and new substance is formed, we term it chemical change. We have examples of chemical change to be the solution of acid hydrides and basic oxide in water is an example of a chemical change. Here, the acid hydride will become an acid proper, and basic oxide, which are actually soluble in water, will become what we call alkaline solution. Is a different thing, even though they behave nearly the same, but in water, there they can actually behave as either acid or a base. The next is the solution of metals in water and acids. The metals we are talking about is highly electropositive metals. This type of reaction is what we call displacement reaction. Here, hydrogen is mostly displaced. Although when we come into this water, the water differs. It might be cold water, it might be warm water, it might be steam. But what we just need you to understand is that it is H2O, whether it is the cold, the warm, or the steam. And when we come to this acid, it depends on the concentration too. And for a metal to displace hydrogen in water or in acid, it means that that metal is highly electropositive than hydrogen. We normally get this thing from what we call reactivity series or electrochemical series of metal or metal ions, respectively. Okay, we go again. We have something we call direct reaction of elements and compound. This is another form of chemical change we do, and all these things we call it reaction, chemical reaction. Remember that each of these we can actually represent it using a chemical equation, although it's not all chemical reaction we can represent with a chemical equation. I just want you to know that. Remember fermentation, and also remember burning is included as change in chemical reaction. Now we need to look into change differences between the two changes that we have actually mentioned, because it is important for us to do that. Easily reversed by ordinary physical means, and chemical change is not easily reversed by ordinary physical means. If you check from the definition, you will understand that, whenever they ask you to differentiate between two things, what you need to do is to first of all give the definition of that. That means that a physical change is a type of change that is easily reversed by ordinary physical means, whereas a chemical change is a change that is not easily reversed by ordinary physical means. Now the next statement there is the substance formed. For a physical change, there is no entirely new substance formed. But when we talk about chemical change, there is entirely new substance formed. It is a temporary change. It is actually a mostly temporary change, whereas for chemical change, it is mostly a permanent change. What we mean by permanent change here is that it's not that we cannot reverse it, but this change will remain like that if we allow it to be. Like rusting of iron. When iron is rust, it remains like that, and it might not be able to come back on its own, except we want to restore it back to what we want it to be. For the physical change, if we remove the change of state, the combination does not actually require a heat change. But to be frank, 99.999% of all chemical reaction requires a heat change. That is actually why it forms a new substance. For physical change, the new material formed is almost like the starting material up to 99%, because if you look at the torn book I have here, they actually look alike very, very much. But when we are dealing with the chemical change, there is no relationship between the new material formed with the starting material. That is when we are dealing with a chemical change. For instance, yes, we might have gas producing gas, we might have a colorless gas producing a colorless gas as a new material, but that particular colorless gas produced in a chemical reaction might not be able to have the same property of the starting material. That is what happened in chemical change. Okay, the new material form is not necessarily alike both in physical and chemical form with the starting material. There are some other statements they normally add up to us that there is no change in mass. Why I don't want to use this to differentiate between the two is that sometimes if we look at the formation of dissolutions, sometimes we might see a change in mass in physical change. Therefore, I do not use that in differentiating the physical and chemical change. Thank you very much for watching this video to this extent.